Like I've already greeted, welcome everybody to another session on redox reactions. We briefly touched on it in a previous session, so I'm going to recap it again from what I showed everybody last week. Okay, now we know that acid-base reactions is the transfer of protons. All right, we know that acid is a proton donor, and it's a proton donor, yes, and bases, sorry, that's the word I was trying to get through. The bases or alkalis, they are proton acceptors. Okay, but with redox reactions, they actually are slightly different, except that protons don't get transferred now in a redox reactions, but rather electrons get transferred. So redox reactions basically are reactions that involve the transfer of electrons. Two types of reactions encompass redox reactions, okay, and first one is oxidation, and the next one is reduction, hence the word redox. All right, a longer term for that would be oxidation reduction, okay, but it is oxidation and reduction combined would just be redox. Oxidation, the oxidation reactions. The original definition of oxidation is the gaining of oxygen. All right, that's the original definition, as I explained last week. But oxidation reactions basically is the loss of electrons. Okay, so electrons are lost in the process. In other words, electrons are produced. Okay, until oxidation occurs, we do not see the electrons. All right, but once oxidation occurs, we actually see the electrons being lost, meaning that they are basically essentially produced. They are on their way out from a particular substance. Okay, so oxidation is loss of electrons. Okay, then we have reduction, which is the second type of reaction, and the original definition for reduction is the loss of oxygen. All right, so oxygen is actually lost. But we define reduction reactions as the gaining of electrons. So while oxidation is the loss, or similarly like an acid that donates a proton, oxidation donates electrons. In that process they lose their electrons, and reduction reactions, or the substance that is reduced, accepts the electrons that the substance that was oxidized loses. And so we form this little acronym called oil rig. All right, oil rig, and this is designed for you to remember this process. So oxidation is loss of electrons, while reduction is gaining of electrons. Put that as NB. All right, very important because this will obviously help you remember this process. We have a little example here, one of an oxidation reaction, all right, and two of a reduction reaction. So the first one, okay, we have magnesium. Okay, for those of us that don't know what Mg is, okay, magnesium, all right, and we see it's been oxidized. How do I know it's been oxidized? Because it's written in the form that shows me that the electrons are being produced. So it's written on the right hand side. In other words, magnesium in its pure form now was oxidized. In other words, I'm showing the process where electrons are lost. Sulfur is being reduced because I'm showing that the electrons are being used. That's why I write them on the left hand side, okay, not on the right. I write the reduction reaction with the substance plus the electrons that it is gaining. In this case, it's gaining 2 electrons, becoming that substance. For oxidation, I show you that the substance, what it was before it was oxidized. Okay, so how I showed you, how I remembered it. Okay, you can take a normal maths addition sum almost, where let's do it like this: 1 plus minus 1 gives me obviously what? 0, right? This eventually becomes 1 minus 1. So I'm showing you how 0 is formed. Okay, but if I do it the other way around, I'm showing you that 0 was actually produced by taking 1 plus minus 1. Okay, this is my little trick that I used when I was in grade 11 and 12, just to be able to remember, because I struggled in the test and exam with actually knowing how do I write which one. Okay, because that's all that we're concerned about in a test or exam. How do we write which one? Okay, and which one is which and how to remember. So I remembered which one was oxidation and which one was reduction from this little trick here. Okay, you can take that's free, if you want to use it or not, it's up to you. Okay, this is essentially what we recapped last week, or what we did last week when I introduced redox reactions, and today we'll be moving obviously a step further. But before we move a step further, there's another process I just want to show you as well, which we also recapped last week. Alright, last week we also saw what actually happened when an iron rod was placed in a solution of copper sulfate, right, which is CuSO4. Okay, hence I obviously split it up into copper Cu2 plus SO4 2 minus. SO4 will always have SO4. Guys, I must just explain this again. I still get this question asked with my other grades as well. SO4 is a substance on its own. All right, this is sulfate. All right, it is a substance on its own. So it is a 2 minus ion substance all the time. Okay, we don't like to, if we separate substances, we usually separate it from what's bonded to it. So if we must separate this, we separate it into copper and sulfate. We don't separate it into copper, sulfur, and oxygen. Okay, it separates from copper into and sulfate because it's if I am correct, it's a polyatomic ion. Okay, there's a whole list of them: nitrates, carbonate, sulfurous, SO3, or sulfur trioxide, not sulfurous acid is H2SO3, sulfur trioxide, I mentioned nitrate already, and I've mentioned carbonate, and of course sulfate. Okay, so now when we put a piece of iron, okay, in a copper sulfate solution, we have what's like a reddish brown, I didn't have brown in my colors, so I only used red, substance that forms as a layer on the iron. Okay, now the iron, if it's left in the solution for a number of hours, all right, the blue color of the copper sulfate solution, it becomes lighter, and the piece of iron becomes thinner. Okay, the piece of iron becomes thinner. So the piece of iron is losing, I wouldn't say it's losing, I would use the word, which is probably incorrect word, but I'll probably get to the correct word soon. It's losing capacity. Okay, it's becoming thinner. All right, it was quite thick. It's losing a bit of its own substance. Okay, so we figured out already that if that's happening, then iron must be being oxidized. All right, because it's losing some of its electrons. All right, it's losing some of its own substance. So our oxidation reaction would be iron Fe, because it came in as Fe, which actually becomes Fe2 plus 2 electrons. Now electrons are negative, of course. Okay, showing that electrons are being produced. Okay, now copper sulfate. All right, copper obviously is copper sulfate being made in a solution. All right, and it's blue. Okay, it's a little blue layer over here. If you thought it was water, no, not water. It's copper sulfate. That becomes noticeably lighter. All right, in other words, it loses some of its blue coloration. All right. Before we jump into what's happening in the copper sulfate, when a piece of copper metal is placed in an iron sulfate solution, all right, no change is observed even after a long period of time. Okay, but if you put an iron in a copper sulfate solution, we definitely see a change. Okay. So the copper 2+ ions, or copper, all right, is being reduced, all right, because the solution is getting lighter. Okay, and this layer over here is copper. All right, this little brownish layer over here. So copper is definitely forming on the iron metal rod. Okay, so copper is definitely forming. So copper in the solution is being reduced to form its metal property again. Okay, so our reduction, all right, because we had Cu2+ in the solution when it was bonded to SO4, we end up having Cu2+ that is gaining electrons, all right, and that obviously is being reduced to just copper metal in this reaction. Okay, now not to go, obviously, we're not done, obviously, we need to still write down the net reaction, okay, because these two, also what we discussed last week, it's what's known as half reactions, right? Half reactions, okay, one half, other half, net will obviously be the full reaction. Now the decrease in the concentration of the Cu2+ ions, okay, obviously shows or is shown by the lightening, in other words, the decrease in the blue color of the copper sulfate solution. Okay, if we must write a net reaction for this, okay, the common factor over here is 2 electrons, so they will cancel out. So my substances that I'm left with on the left hand side is iron metal plus the Cu2+ ion, all tends to the iron 2+ ion plus copper metal, which is just Cu. Now the question on everybody's mind is probably what has happened to SO4, alright, but more so what's happened to SO4 2-, because sulfate was definitely involved in this reaction. Okay, it was not involved in this reaction, as in other words, it's partaking in the reaction. It was involved in terms of it was part of the solution, all right, which was part of the reaction. But SO4 2-, there's a name for this, all right. SO4 2- is known as a spectator ion. Okay, spectator, there we go, spectator ion. Okay, in other words, it doesn't partake in the redox reaction, all right, it doesn't partake in the oxidation or reduction. In other words, it doesn't undergo oxidation and it doesn't undergo reduction at all. It's just watching this whole process happen. So no oxidation and no reduction reaction occurs with SO4 2-. What we want to have a look at today is oxidation numbers. Okay, I want to have a look at is oxidation numbers. Okay, let's take for example hydrochloric acid, which is HCl. Okay, maybe let me write my Cl a little closer. HCl, hydrochloric acid. We are very familiar with HCl. Okay, we've used it a lot in acids and bases section, but more so we also have been using it throughout our chemistry journey since grade 10. So we all should be very familiar with HCl. Now, something about HCl that we must understand is that it's broken up obviously into hydrogen and chlorine. Okay, this is not the reaction, of course, but we do know that hydrogen is in the first group, and we know the first group has a positive value to it, or positive valence electron to it. So we know that hydrogen is a positive ion, right? It's a positive substance, while chlorine is a negative substance. Okay, so for oxidation number, hydrogen should have an oxidation number of +1, while chlorine should have an oxidation number of -1. Okay, and how do I know this? The ions tell me. Okay, the ions tell me. Okay, in other words, it tells me the state of the oxidation. Oxidation numbers tells me the oxidation state. Okay, tells me the charge. Okay, so an oxidation number, oxidation state of an atom in a molecule, okay, remember these are both atoms, okay, is the charge it would have if the electrons in each of the bond belonged to the more electronegative element. Okay, so hydrogen belongs to the more positive, while chlorine belongs to the more negative, indicated by the charge of the ions. Okay, it's indicated by the plus and the negative. Okay, now HCl, when it is written as a molecule, we don't see any number appearing here. All right, no, we don't. Okay, so oxidation numbers, okay, for this molecule must add up to 0. And I can see that happening, okay? Because if hydrogen has a value of +1 and I add it with -1, what do I get? I get 0. So oxidation numbers, first rule, all right, must always add up to 0 if it's a molecule. All right, so I would like to call rule number 1. All right, in a molecule, the oxidation numbers must always equal 0. Another rule of oxidation numbers, okay, we do know also that hydrogen and chlorine, if in the reaction state, so if I had hydrogen plus chlorine, I would obviously get HCl, and I would obviously have to balance the numbers there. Okay, so these are what is called uncombined elements. All right, they are bonded just to themselves. Okay, they are not bonded to any other substance. They're just bonded to themselves because they can't exist alone. So for any uncombined element, all right, as we see here, so with hydrogen, chlorine, and amongst others, the oxidation number is also 0. Okay, fantastic. Now what happens if we have, okay, actually I'll save that for an example a little bit later. Okay, but basically with oxidation numbers, they do provide us with a convenient way of following the transfer of electrons during reactions. Okay, so in other words, if we have a reaction, and how we're going to ask this in a test or exam is we're going to give you a reaction, and we're going to give you the oxidation numbers of either one or few of the substances, and we're going to ask you to find out the oxidation number of a particular element or atom in the reaction. There are a couple of more rules, so I'll just give them to you quickly. If I have an oxidation number of an ion of an element, all right, that means that if I have, for example, Cl minus, all right, just for example, or if I have, for example, SO4 2 minus, okay, then the oxidation number of an ion or element is the same as its charge. So if it's 2 minus, then that means my oxidation numbers must add up to -2 and not 0, because for an ion of an element, the oxidation numbers must add up or must equal to the same as the charge on that ion element. Another rule that also exists is that the sum, which I've just said, this I've already mentioned this one, but I'll mention it again. It's on my list here. Sorry, I wrote down the sum of all oxidation numbers in a compound ion. All right. So in a compound ion, which would be something also like this. So I'm going to echo this. In a compound ion, basically it's equal to the charge on that ion, which in this case was -2. Okay, it's almost basically the same thing. The oxidation number of the halogens, all right, when the compound consists of two elements, all right. So for the halogens, the oxidation numbers are always equal to -1. That is a rule that exists. Fortunately, it must be followed and it must be applied. The oxidation number of oxygen in a compound, okay, so of oxygen when it's in a compound, in other words when it's bonded to other elements, is always equal to -2 in a compound, oxygen only. Okay, and the oxidation number of hydrogen, also hydrogen in a compound, all right, is always equal to +1. Now let's say for instance we have an example when they ask you what is the oxidation number, all right, so I want to know what is the oxidation, that's a Q, let me take the Q away. What is the oxidation number, okay, of nitrate, all right, or actually let's switch it up. What is the oxidation number of nitrogen in the nitrate ion, which is NO3? The oxidation number of nitrogen in NO3, all right, which is obviously in nitrate. Okay, now nitrate, as I've already written it, let's use another color, maybe let's use green, right, is NO3 minus. Now the sum of all oxidation numbers in a compound ion is equal to the charge on that ion. What is the charge on this ion? It's just negative without a number, and if it's just negative without a number, we know it's -1. Okay, that's what we know. They also told us that the oxidation number of oxygen in a compound is nearly always -2. Okay, so basically what they are saying here is that, well, the oxidation number, and I'm going to shorten it to just ox, NO, oxidation number of nitrogen, all right, plus 3 times that of the oxidation number of oxygen must equal -1. Okay, reason why I say 3 times that, because it's NO3. Okay, so let's figure this out. Therefore, when it comes to now sub it in, the oxidation number of nitrogen is still unknown. Okay, we want to add that to 3 times -2. And that must equal -1. Okay, well, the oxidation number of nitrogen is still unknown. Let's keep that in brackets for now. Plus, well, 3 times -2 gives me -6. And that's still equal to -1. So I end up with oxidation number of nitrogen -6. Well, I take the 6 over. Therefore, I end up with the oxidation number of nitrogen, all right, in nitrate to equal +5. All right, and I can test that. All right, and the reason why it becomes +5, the -6 over here goes over to that side because it's separated by minus sign. So positive times the negative will become a negative. You take it over because it's separated by minus sign. It becomes -1 plus 6, which gives me obviously +5. It's the same as 6 minus 1, basically. Therefore, I can check that in this equation. Well, if I say 5 plus -6, okay, this is a check. Say 5 plus -6, guess what? It ends up with 5 minus 6, which equals to negative 1, and that's what I had to begin with. So therefore I know that this answer is 100% correct for being the oxidation number of nitrogen in nitrate. So let's apply the same logic here with example number 2, where I want now the oxidation number of nitrogen, but now no longer in NO3, but rather in nitrite, which is NO2, and it's also an ionic compound, and it has a negative charge on it. Okay, so now let's go ahead and do this. Let's approach it the same way. So basically, the oxidation number of nitrogen plus the oxidation number of oxygen, in this case there's 2, so twice that of the oxidation number of oxygen must equal to negative 1. Okay, we can handle this one out, okay, because we know that there's 2 oxygens here, and we know the oxidation number in a compound is always minus 2. So plus 2 times minus 2 for this one must equal negative 1. And here we still have the unknown value of nitrogen, oxidation number of nitrogen rather. Okay, we know 2 times negative 2 is minus 4, so we end up with plus minus 4, which becomes oxidation number of oxygen minus 4. We know we can carry over this entire number to the side, okay, which does equal obviously to minus 1 plus 4. Okay, and therefore the oxidation number of nitrogen is equal to positive 3. If I perform a check, if I have positive 3 plus minus 4, I end up with 3 minus 4, which is equal to negative 1. I know this answer is 100% correct. So here we have a certain reaction between sodium hydroxide and hydrochloric acid, and obviously showing the product that has formed, which is the salt plus water. And the question here is to determine whether or not the reaction is a redox reaction or not. Okay, so how are we going to go about doing this question? Well, first we're going to need to determine and establish what the oxidation numbers in each of the following elements are. So we know for hydrochloric acid, okay, we know hydrogen is always positive, halogen is negative. All right, so we've got minus 1 for chlorine, positive 1 for hydrogen. For sodium is also in positive 1. The positive 1 group is also in the same group as hydrogen, but I'm not going to start there. I'm going to start with my oxygen, because oxygen is always minus 2. So oxygen is minus 2, and I know that this entire compound must give me 0. Okay, it's not ionic, but I know this entire compound must give me 0. So I got minus 2, so only thing that's going to give me 0 is if I have 2. Well, sodium is in the same group as hydrogen, so that also gets positive 1, and hydrogen is always positive 1. So positive 1 plus 1, positive 2 minus 2 gives me 0. I know I have given the correct oxidation numbers for both the acid and the base. Come to the products, same thing. I know chlorine is minus 1, sodium is positive 1, which I established on that side. Okay, we know that for hydrogen, the oxidation number is plus 1, but I have 2 of them, so it's 2 times plus 1, and the oxygen is minus 2, and both of these also give me 0. So looking at whether or not the oxidation numbers has changed. Let's run through it quickly. Hydrogen here was +1 and +1 there. It's still +1 on the product side. Chlorine was -1 in the as a reactant. It's still -1 as a product. Oxygen is -2. Oxygen is still -2. Sodium was +1. Sodium still +1. So we can clearly see that none of the elements have changed oxidation state. All right. So none of the elements, all right, have changed, right? And this is how we would state our answer: have changed the state of oxidation, or we can say none of the elements have, none of the elements' oxidation numbers have changed, or we can say it like this: therefore, not redox, or we can say not a redox reaction. Okay, and that's how we can determine, of course, whether or not it is redox reaction or not. So here we have the same question, different reaction. We want to know if it's a redox reaction or if it's not a redox reaction. Okay, if FeCl3 plus water plus SO2 gives us sulfuric acid H2SO4 plus hydrochloric acid, which is HCl plus FeCl2, and we can see we've balanced the equation, as you can see by the underlined 2's. Okay, those are the balancing numbers. Okay, so what we need to do is we always need to find out or identify the oxidation numbers of each one. Now the oxidation number of chlorine is -1. Yes, I know there are 3 of them, okay, but this 3 doesn't have anything to do with the fact that chlorine's oxidation number is always -1. Okay, so in brackets we'll have -1 times 3, which we know is going to give us -3. So the oxidation number of iron now must be +3, and that will give us 0. Water, the oxygen element is always -2. Hydrogen is always +1. Okay, and I have 2 hydrogens. Therefore, I know I'm going to get 0. +2 minus 2 gives me 0. Oxygen is always -2. Yes, I know I have 2 of them. Okay, so if I have 2 of them, I get -4. Therefore, the oxidation number of sulfur in SO2 must be +4 to give me 0. Again here, hydrogen, always +1. I know I have 2 of them. Sulfur, I don't know yet, but I know oxygen always has -2 times 4. Okay, so oxidation number now of sulfur, in order for me to still get 0, I have +2 and I have -8. I know that in order for me to get 0, I must have 8 minus 8. So I have -8 and +2, so my missing oxidation number for sulfur must be +6. +2 plus +6 gives me 8 minus 8 gives me 0. I know my oxidation numbers is correct. Hydrogen and chlorine in HCl, +1. This 2 has nothing to do with the oxidation number. It's just the balancing number. That's -1. I get 0. Iron over here, chlorine is -1, even though I have 2 of them. So I have -2, so iron now must be +2 for me to get 0. What I can identify here, ladies and gentlemen, is that the oxidation numbers has changed for iron. It was +3, it's now become +2. Oxidation numbers also changed for sulfur. It was +4 and now it's +6. So in my answer, right, and how I orchestrate it, okay, we know that iron, right, has changed from +3 to positive 2. Alright? And sulfur has changed from positive 4 to positive 6. Okay? Because there is there is a change of charge, right? Or in the charge. There's a change of charge, therefore redox reaction. Done. Nothing to it. Alright? You can see because there's a change in the charge, or because there is an increase or decrease in oxidation number of more than one element in this instance, we can definitely see that this is definitely a redox reactions by using oxidation numbers. So oxidation numbers do help us track the transfer of electrons between elements within a reaction. Thank you so much, grade 11s, for joining me today in our session on redox reactions. This concludes the topic of redox reactions, and I hope you've all have understood, hope you've all have grasped the concepts, and this is a very nice section in tests and exams to score marks on. Thank you so much for joining me once again, and I'll see you for another topic soon. Bye bye.